So good morning. In our last classes, we have been discussing about the different types of filters and how we can design those filters. We have discussed, right? So we have already discussed, see, Fourier series method without using window, Fourier series method using window method. Then yesterday we have discussed frequency sampling method, which is nothing but Fourier transform method itself. Okay, and we have discussed without using the window. Okay. The next is your Fourier transform method using window. It is similar to that what we have done over here. Okay. So I am not going into the details. After you get the HN, you also calculate the window functions, multiply it, and the rest of the process are same. So I am not going into that. Okay. So today we will basically be discussing about the new type of this window, Kaiser window, which I already told. In the previous cases of the windows, if you see over here, I have already told you that the top five this windows, that is the rectangular window, Bartlett or the triangular window, Blackman window, Hamming window, Hanning window, they already have a fixed equation, right? So we need not to worry about the order of the filter and other parameters of the filter. However, under ideal condition, it is not the case. It should not be the case because when we are talking about this kind of windows, when I am designing a filter of say order 10, the filter characteristics would be different. When I am trying to design a filter say of the order of 20, its filter characteristics would be say different, right? When I am designing a filter with an order of 30, its characteristics will be different, right? So as we change the order of the filter, there is a change in the parameters of the filter. So whatever the previous this window functions we have discussed, they are not taking that into account. Hence, there is a need to look into a type of window where we can uh, set the window parameters as per the filter characteristics itself. Okay. Yeah. The other type of windows which are having the fixed equation, it is something like that, one size fits all. Okay. Agar if you look into that one size fits all, I am a heavy person. If I take that side, it might be pretty okay for me. But if someone else wears who is leaner than me, it will not look very good on him, right? So depending upon the characteristics of the filter, this window function or the equation should change. Okay. So in this regard, we have this Kaiser window function, which for which the parameters have to be decided. These window parameters are to be decided based on the characteristics of the filter what we want to design. Okay, so that is the thing. So when we are discussing about the characteristics of the filter, so let's see the thing in the this frequency response of the filter. So under ideal condition, what we have discussed, that for a low pass filter, this is omega, this is modulus of h of omega, right? So for an ideal low pass filter, it is something like this. Omega c is there. So 0 to omega c, you have a pass band and then you have a stop band. But this is an ideal filter, and we have already discussed when we try to design ideal filters, then we need infinite number of sinusoids to recreate this filter, what you call, characteristics, right? Under practical considerations, it is not possible. Under practical considerations, it is not possible. Okay. So, what happens under ideal conditions? So, say for example, I am now getting into this frequency response. We have discussed that the amplitude in the passband is having an amplitude of 1. Amplitude of the this modulus of h omega in the passband is equal to 1. We have already discussed for the FIR case. So let us take this case. So here we are having the value of 1 in the passband. In the stop band, ideally it should be 0, but usually it is not 0. We have a baseline which we call it as H2. H1 for the passband, H2 for the stop band. H1 is the amplitude or the magnitude of the response of the filter in the passband, and H2 is the magnitude response of the filter in the stop band. Okay. Now, as I was telling that it is not possible to have infinite number of sinusoids to recreate that filter. Okay, so we are basically having say 10 order filter or 20 order filter or 30 order filter. In between also it's possible. Whatever the order you want to fix, you can get that. So over there, what you are doing, you are limiting the number of the sinusoids basically. Okay, you are limiting the number of the sinusoids over there. Now there should be a non-idealness in this amplitude response, right? So it will not be idealistic in nature, it would be and non-ideal in nature. Now how do you find out that non-idealness? In the Fourier series, if you remember, we have discussed that we get some sinusoidal wave-like structure where there is a plane, this thing, right? We discussed or not? Oh, then why you are putting all of you a blank face? So, because of this, what is happening? This sinusoidal like structure, instead of having this H1, we get this sinusoidal like pattern, and these patterns they are called ripples, and the ripples in the passband they are called passband ripples. Okay, so if you see from the ideal nature, we get a deviation in the positive side and a deviation in the negative side, and that boundary it is given by 1 plus delta 1 and 1 minus delta 1, and this total weight it is called ripple weight. So if it is in the passband, if these are the passband ripples, then we call passband ripple weight, and it is given by 2 of delta 1. Similarly, in H of 2 also we can get a stop band ripple weight which is given by 2 of delta 2. Okay. Then we have the passband from 0 to omega 1. We have the passband up to here. So from where? So what we will be taking this as the omega 1? Omega 1 will be taken from the point where the amplitude response is linearly decreasing. Okay, or in other terms, so we can say the roll off is starting. The roll off is starting. Roll off means the slanting line which is decreasing. Okay, and then where the roll off ends, that point is regarded as omega 2, and from that point our stop band ripple it starts. Okay, and how do you find out omega c? Omega c is given by omega 1 plus omega 2 divided by 2. Okay, and this is the frequency range in between omega 1 and omega 2. It is given by transition band. It is given by transition band. Okay. So now you have understood about the filter characteristics, right? Now similar would be the filter characteristics for the high pass filter, low pass filter, high pass filter, band pass filter, band reject filter. Over there also you will be getting this kind of thing. If you have any confusion, you please come to me. Okay, so I am not covering that thing. Now let's take an example with the Kaiser window. Okay, so in the Kaiser window, what we have is that design an FIR low pass filter satisfying the following specification. Okay, design an FIR low pass filter satisfying the following condition. Alpha P is less than equal to 0.1 dB. Alpha S it is greater than equal to 44.0 dB. Okay, so that is stop band ripple. Alpha P is pass band ripple. Omega P pass band frequency 20 radians per second. Omega is stop band frequency 30 radians per second, and sampling frequency here, since we have used S as the for the stop band ripples, here we are giving SF as the sampling frequency. Otherwise, usually you have seen that we are using omega as for the sampling frequency, right? So here, to distinguish the same from the stop band frequency, we have given omega SF for the sampling frequency, and the sampling frequency is 100 radians per second. Now the transition width B is omega S minus omega P, just minus कर देना है, so that is 10 radians per second. Omega C, I already told you how to find out. You are given with omega P, you are given with omega S, just average it out and you get the omega C. Okay. Then we need to normalize the frequency. So omega C will be represented with omega C T, which is nothing but omega C by 2 pi sampling frequency. We have already discussed 2 pi cutoff frequency by sampling frequency, right? So if you do this, so you get pi by 2 radians is your cutoff frequency, right? Is your cutoff frequency. Okay. Now in our previous cases, if you see, we were not discussing about this omega p, omega s, and all these things. Okay. Now you think of a condition. Here you are having 20 and 30. Okay. So if you reduce 10 over here, reduce to 10 and you increase it to 40. Again you get the same thing. So there was some fallacies over there, right? So cutoff frequency, so we are not dealing with those things. Now here if you see, we are dealing with this passband ripple, this thing, what is the transition weight, okay? So all of these are taken into account while we are designing the filter. This was not the case in the examples where we were, which we were discussing till yesterday, right? So this is the power of the Kaiser window. Kaiser window allows you to design customized FIR filters. Okay. Now next step is step 1. We have to find out the transfer function characteristics h of e to the power j omega. So 1 in the region of 0 to pi by 2, just like this one. We discussed this. HDN we can find out. So step 1 complete. It's similar to the previous case which we have discussed in the Fourier series method, or the Fourier series method. Now the next step is figure out delta 1 and delta 2. Okay, figure out delta 1 and delta 2. So what it is given. So if you consider a constant which is equal to a, this is given by 10 to the power 0.05 into alpha p. Okay, so what is delta 1 basically? So delta 1 is equal to a minus 1 divided by a plus 1. This is what, if you see, 10 to the power 0.05 multiplied by alpha p over here. So we are having this alpha p 0.1. So a minus 1 divided by a plus 1. We got a value. Then for the delta 2, which is in the stop band, this is nothing but 10 to the power minus 0.05 into alpha s. Okay. So this is what we have done over here. Delta 2 equals to 10 to the power minus 0.05 within bracket 44. So we got the value over here. Right. Now we have to find out delta. So what is this delta? Delta is nothing but minimum of delta 1 and delta 2. Okay. So which is the minimum one? This is the minimum one. There are some questions some students have asked previously. What happens if your delta 2 is the minimum? Yet delta 1 is the minimum. What happens if delta 2 is minimum? If delta 2 is minimum, in the next step, you see we are calculating normalized alpha s. So in that case, alpha s would be the delta 2 directly. Okay, alpha s will be replaced with delta 2. However, in this case, we are having delta 1 as the minimum thing. So here we have to put minus of 20 log 10 delta, which is equal to 44.797 dB.
Why is it happening that when data 2 is minimum, we are taking alpha is
So it is the method basically. So certain things you do as per the what do you call whatever is given to you, how to approach a numerical. So so I also don't know basically that thing. So one of the reasons maybe if you see here also, you see the delta s, this alpha s, it is basically 44.797, and if you see over here, this is the thing. So maybe this is the reason that when we have this thing, so they are taking this alpha is nearly equal to this delta 2 maybe, but this is what it is followed. Okay. So from there, after we have done this, we have to calculate the shape parameter. Okay. We have to calculate the shape parameter. Now the shape parameter alpha, it is equal to 0 for alpha is less than equal to 21. Okay, the shape parameter is 0.5842 multiplied by alpha is minus 21 to the power 0.4 plus 0.07886 alpha is minus 21. Okay. If our alpha is in the range of 21 and greater than 21 and less than equal to 50. Okay. In the next step, we have 0.1102 alpha s minus 8.7 for alpha s greater than 50. So, our case, it is suitable for the second equation. So, we get this, put the values of alpha s what we have got, and you calculate the shape parameter. Then calculate the shape parameter. Once you are done, then we have to calculate the parameter d. Then we have to calculate the parameter d. Now d is equal to 0.9222 for alpha s less than equal to 21, and it is equal to alpha s minus 7.95 divided by 14.36 for alpha s greater than 21. So d is equal to this one, because our alpha s, it was greater than 21. So this equation was used and we can get the capital D. Okay. So first we have, what we have done? We have calculated the amplitude response. Then what we have done? We have calculated the delta. Using that delta, we have calculated alpha s. From that alpha s, we have calculated the shape parameter, and then we have calculated the parameter d. Okay. Now, from this parameter d, we have to calculate the filter order or length. So length is given by, length is greater than equal to sampling frequency d divided by b plus 1. So omega s, you know, d you have calculated, b also you have calculated here, right? So you calculate, and it is 26.66. So it is greater than equal to, so always greater than that 27. Okay. So suppose it is 27.66, we can take it as 28, no doubt. But till now, whatever the uh, what you call numericals we have done, we have seen that if we take the length as the odd one, then it becomes easier for us. So we can take it as, say, 29, because the equation says greater than equal. Okay, nothing else. Okay, just for the sake of our convenience. So from here, we have to calculate window sequence. India's window sequence for the Kaiser window, it is given by Wn, it is equal to I0, which is basically Bessel polynomial function of alpha under root of 1 minus 2n by capital N whole square divided by I0 alpha. Okay. Capital N by 2, we have already seen that. So from there we can less than equal to n by 2. So we can vary the value of this thing. So I think it was 27. Yeah, we have taken as 27. So see 13, 13, 13 plus 13, 26 plus W0, 27 number of window functions we have to calculate. Okay. Now herein if you see I0 of alpha under root of 1 minus 2n by capital N. Capital N already we have calculated whole square, right? This is it. So you will be getting for each and every level, you will be getting this value. If you call this as x, for every x, we will be having a value of I0x. Okay. Suppose here, if you see 3.9406, for this we will be having a specific value. So a table will be given, which is called Bessel polynomial function table. I forgot to bring that table over here, so I will share that PDF file to you next. So for each x values, you will be getting some I0x values. So if you see, for W0, this n is equal to 0, so this portion becomes 1. So we get I0 alpha by I0 alpha, hence it is 1. For other things, you have to calculate in this fashion. Now find Hn from here. You have to calculate the Hn. Okay. Then find the Hn.